Hey everyone, and welcome back to the channel. For centuries, humanity has gazed at the stars, seeking answers, finding comfort in the predictable dance of celestial bodies, and slowly, painstakingly piecing together the grand cosmic tapestry. We've mapped the solar system, ventured to other worlds, and peered back in time to the very dawn of creation itself. Our understanding of the universe, once a realm of myth and speculation, has solidified into a grand, elegant, and largely consistent scientific model. We have a story. A Big Bang, an expanding universe, galaxies forming from tiny quantum fluctuations, governed by the precise laws of physics we've so diligently uncovered. It's a magnificent narrative, one that gives us a sense of place and purpose within an infinite cosmos. But what if I told you that this beautiful, coherent picture, this bedrock of our cosmic knowledge, might be riddled with fundamental glitches? What if the universe itself is sending us signals, subtle yet profound, that our most cherished assumptions are, in fact, dramatically incomplete or even utterly wrong? What if the very fabric of reality, as we understand it, has a tear in it, revealing something far more bizarre, more unsettling, and ultimately more awe-inspiring than we ever dared to imagine? Our journey into these potential universe glitches begins, paradoxically, with what many consider the single greatest triumph of modern cosmology, the cosmic microwave background, or CMB. Imagine a snapshot, a baby picture of our entire universe, taken just 380,000 years after the Big Bang. That's essentially what the CMB is, the faint, uniform glow of radiation permeating all of space, the afterglow of a universe too hot and dense to allow light to travel freely. Before this point, the universe was an opaque, scorching plasma. As it expanded and cooled, electrons and protons finally combined to form neutral atoms, and suddenly light was free to escape. That ancient light, stretched and cooled over billions of years of cosmic expansion, is what we detect today as microwaves. It's not just a relic, it's a blueprint. The CMB is almost perfectly uniform, demonstrating that the early universe was remarkably smooth. But crucially, it also contains tiny, almost imperceptible temperature fluctuations, ripples in the fabric of spacetime. These minuscule variations, measured in millionths of a degree, are not noise. They are the gravitational seeds, the primordial density enhancements, from which all the galaxies, stars, and ultimately us, would eventually form. The standard cosmological model, particularly the theory of cosmic inflation, beautifully explains these fluctuations, predicting their size, distribution, and statistical properties with incredible precision. It's a testament to human ingenuity, a cosmic Rosetta Stone that seems to tell us everything we need to know about the universe's beginning and its subsequent evolution. Or so we thought. Because hidden within this seemingly perfect cosmic blueprint are anomalies, features that stubbornly refuse to conform to our elegant theories. They are the smudges on the baby picture, the pixels that don't quite fit the pattern, and they hint at a reality far stranger than our current models allow. First, and perhaps most famous, of these cosmic glitches is known as the *** cold spot. Discovered in 2004 by scientists analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the European Space Agency's Planck satellite, the cold spot is exactly what it sounds like. An unusually large, unusually cold region in the CMB. It spans about 5 degrees across the sky, an area roughly equivalent to 20 full moons. While the CMB naturally has hot and cold spots, those crucial fluctuations that seeded galaxies, the cold spot is statistically improbable. Its temperature is significantly colder than expected, and its sheer size is baffling. If our standard cosmological model is correct, a fluctuation of this magnitude should occur with a probability of less than 1 in 50,000, some estimates even putting it closer to 1 in a million. Imagine rolling a die and getting a 6 1,000 times in a row. It's not impossible, but you'd start to suspect the die, or the game, was rigged. Scientists, understandably, have tried to explain away the cold spot. The most conventional explanation proposed that it might be a supervoid, an incredibly vast region of space containing far fewer galaxies and much less dark matter than average. Such a void would create a gravitational, cold spot through a phenomenon called the Sachs-Wolf effect, where photons lose energy as they climb out of the shallower gravitational well of the void. While supervoids do exist, extensive surveys have failed to find a single, coherent supervoid massive and empty enough to fully account for the observed temperature depression of the cold spot. The largest supervoids discovered, while impressive, simply don't have the gravitational punch to explain the anomaly's extreme coldness and immense size. The search for a suitable supervoid has continued for years, yielding some candidates, but none definitively matching the required parameters. It's like searching for a giant in a crowd and only finding a particularly tall person. It's a step in the right direction, but not the whole story. So if it's not a supervoid, what else could it be? This is where the universe starts to whisper truly radical possibilities. Even more unsettling than the cold spot is another CMB anomaly, colloquially dubbed the *axis of evil. This refers to an unexpected alignment in the large-scale distribution of temperature fluctuations in the CMB. Specifically, certain large-scale patterns of hot and cold spots appear to be aligned with each other, and bizarrely, with the plane of our solar system, the ecliptic, and even the Earth's velocity through space. Discovered initially in WMAP data, and largely confirmed by Planck, this alignment is statistically unlikely to be a random coincidence. Our cosmological models, based on the fundamental assumption that the universe is isotropic, meaning it looks the same in all directions on large